Dadapatil Rajale Arts, Science and Commerce College, Adinathn, Patil. I, Professor Darandale Jayashree P.Darandale, I welcome the Principal of the College, Dr. R.J. Temkar sir, today's resource person, Professor Hamid Sayyed, all the faculty of our college, and all the participants. Now I request Professor Sanjay Maske to make introduction about the college and today's webinar. Thank you.
Good morning. Good morning, everybody. Shri Dadapatil Rajale Shikshan Sanstha, Dadapatil Rajale Arts, Science and Commerce College, Adinathn, Taluka, Pathardi, District, Ahmednagar. Department of Computer Science organized national level webinar on basics of digital electronic science. Our college, Dadapatil Rajale Arts, Science and Commerce College, has been established by Honorable late Dadapatil Rajale Alais Bhau in 1991. The college is located in rural area and majority students are the members as sugarcane cutting workers. The vision of the college is to impart knowledge and skill in rural youth for creating strong human resources needed for building nation. Our college is dedicated to provide education for all with its mission to bring up deprived section into mainstream of higher education to accomplish its mission. We have taken great efforts right from the campus development to student satisfaction. Our college provides learner-centric atmosphere with the help of ICT-based resources which are valuable in such post-pandemic period. The well-equipped laboratories and library, gymnasium, indoor and outdoor stadium, competitive examination guidance center, and NSS unit of college involved various activities of the college and outreach programs. The college offers various courses for students. It offers 5 academic programs, graduate level, 2 at postgraduate level science stream, and 6 programs in arts and commerce stream. Today's webinar of Chairperson Professor Hamid Sayyed, Ghule College at Ahmednagar will be helpful all students, teachers and parents basic of digital electronic science. Now I request Mr. Darandale to continue further program. Thank you.
These opportunities and request Professor Yogita R.Ingale to introduce today's resource person, Professor Hamid Sayyed.
Hello everyone and welcome to today's session. Today is a national level webinar on basics of digital electronic science organized by Department of Computer Science in Dadapatil Rajale Arts, Science and Commerce College, Adinathn. I would like to introduce today's resource person, Professor Hamid Sayyed from Ahmednagar. He has completed higher education in electronic science. He has qualified in SET in electronic science. He is a well-known person in the higher education. Professor Hamid sir is currently working as the assistant professor in Department of Computer Science at Marutraoji Patil Arts, Commerce and Science College, Ahmednagar. Professor Hamid sir is also working as NAC-IQAC coordinator in Marutraoji Patil College in Ahmednagar. He has designed a project of automatic college where he has designed class FYBCS and SYBCS lab kits, lab manuals. Professor Hamid sir has participated in various seminars and conferences in India. He has completed number of certificate courses Friends, today we have a very distinguished person. I once again welcome Professor Hamid Sir and all participants of this webinar. I'm sure today's webinar definitely will give you information on basics of digital electronic science. I conclude my introduction and thank you once again. Thank you.
Now, without wasting a time, I request today's resource person, Professor Hamid Sayyed, to deliver his speech. Over to Professor Hamid Sayyed, sir.
Good morning, everyone. Hello. Good morning, everyone. I am really very happy to be with Dadapatil Rajale College faculty and the audience at the national level. Okay, we will start our session, Basics of Digital Electronics. So, the digital electronics is a field, very vast field, and we can take today today's seminar on only basic topics of digital electronics. So, first of all, we see the introduction of digital electronics. So, electronics circuits are classified into two broad categories. One is digital and other is analog. Uh, The digital electronics involves quantities with discrete values, whereas analog electronics involves quantities with continuous values. The word digit comes from source Latin word digit or digitus. That is Latin word for finger. And as a finger are used for discrete counting, an analog quantity is one having continuous value. A digital quantity is having a discrete values, as we see in this graph. Most of physical quantities appearing in the nature, such as temperature, light, humidity, atmospheric pressure, are in analog nature. If we consider temperature of a given day, it does not go from 40 degrees centigrade to 41 degrees centigrade. Rather than it takes all infinite values in between. However, instead of recording temperature on the continuous time basis, uh, if we take a temperature reading on every hour or a discrete time period, we will get discrete values of the temperature. So we will see figure 1 A is an analog representation, whereas continuous time temperature temperature continuous time continuous reading is taken by us, and in figure 1b the temperature is recorded after an hour and it shows discrete values. So some advantages of digital data over analog data. It is found that digital data can be processed and transmit more efficiently and reliably than analog data. The digital data can be stored more compactly and reproduced with greater accuracy and clarity than when it is in analog form. Besides this, some of the more important reasons for the widespread use of digital techniques and systems are the following. The basic building blocks used in digital circuits operate in the one of the two state known as on and off. So, which results in a very simple operation. There are only few basic operations in digital circuits which are very easy to understand. The logic involved in digital techniques is based on Boolean algebra, which is quite simple to understand. The large number of ready-to-use electronic circuits in the form of single chip known as IC integrated circuits are available for performing various types of operation. They are highly reliable, accurate, and small in size, and the speed of operation is very high. Digital circuits are highly suitable for computers, calculators, telephones, etc. We will see the digital display uh, or the display of digital data is very convenient and elegant. Digital systems or digital electronics contains circuits and systems in which there are only two possible states. These states are represented by two different voltage levels, usually referred as a high voltage or low voltage level, high level or low level. The two states can also be represented as represented by switch, that is open switch or closed switch, or with lamp, which is lamp is on or lamp is off state. Such two state system are called as a binary system. So some merits and demerits of digital system. Now we can say that a digital system is a combination of digital circuit. So with a combination of digital circuits, various digital circuits, digital system is made in which information is processed in discrete form rather than its continuous form. In digital system, the amplitude can take only discrete values, either zeros or 1. Some of the example of digital systems is digital audio, digital video, digital computers, calculators. The world's largest digital system is the telephone system. So some advantage of digital systems are easy to design. The values of voltages can be determined earlier as the basic operation of the logic circuit known. Fluctuations in the voltages have no effect on the digital systems as the exact value of the voltage is not so important. Throughout it is prone to noise and attenuation, it can be easily overcome. So noises in the digital system are very low. The storage and retrieval of the information is much easier to implement. It is less sensitive to device parameter and it is more reliable. Built-in error detection and correction can be used in digital systems. The digital technique is flexible as they can be easily programmed to implement any algorithms. So some of the demerits of the digital system is the major demerit of digital concept is the real world information is mainly in analog nature and which has to be converted into digital nature. Means suppose we want to sense temperature and convert it into digital form. So temperature is in the analog quantity. So temperature is sensed by sensor, and it can be converted into uh, digital form by analog to digital converter, and then that digital data is processed. So this figure can show that analog data is converted to digital data by some digitizer called as analog to digital converter. This digital data then be processed by modulator or coder, such as his amplitude is changed or noise is reduced, etc. Then demodulator demodulates the digital data into its original form, such as analog data, and this analog data is our original information. So this type of diagram is used in transmission of analog information. The binary system uses symbols 1 and 0 called as binary bits. The two different voltage levels are used to represent the two bits. The binary system uses 1 and 0. Uh, Normally, 1 is represented by the higher voltage, which is referred as high, and 0 is represented by the lower voltage, which is represented as low. The voltages used to represent 1 and 0 are called logic levels. In general, voltage range voltage range is specified or assigned to represent logic levels rather than assigning a single voltage. Digital signal representation is here. uh, the figure shows there is acceptable TTL gate input signal levels. There is input side when we say the voltage is in between 2 to 5 volt for a TTL gate, then it is referred as high, and voltage in between 0 to 8 volts for input side, it is referred as low. Whereas at the output side, the voltage from 0 to zero point 0.5 is referred as low, and 2.7 volt to 5 volt is referred as high. So any voltage between specified minimum value and specified maximum value. Similarly, low can be any voltage between specified minimum value and specified maximum value. So basic block of a digital circuit is a basic logic gates, whereas binary input signal is given to it, and one binary output signal is produced at the output. So basic types of logic blocks are combinational logics and sequential logic blocks. The combinational logic blocks whose output present output is depends only on its input logic, and whereas a sequential logic block whose output logic values depends on the input values and the present state stored information of the blocks. Means uh, sequential circuits are those whose output depends not only on the present input but also depends on past output. Functions of gates can be described by truth table, Boolean function, and K-map. So these are the basic building blocks for the digital systems. First one is the AND gate. The symbol is this. There is a two inputs A and B. Generally, when there is a two inputs, whereas three inputs, four inputs AND gate are available in the market. But generally we referred as the two inputs A and B, whereas X is the output. So X is equal to A dot B or A into B is the function of the AND gate. Then truth table is 0 0 0 0 1 0, means anything into 0 is 0, just 1 into 1 is 1. Then OR gate, there are again two inputs and one output X, and X is equal to A plus B or A or with B. uh, then truth table is whenever it is 0 0, both the inputs are 0, X is equal to 0, otherwise X is always 1. Then third gate is inverter. I only write is here I. So this inverter or NOT gate, uh, there is only one input and one output. The output is always inverted the input. Means if input is 1, output is 0, input is 0, output is 1. Fourth gate is buffer. Uh, in buffer, input follows output, output follows input. Fifth gate is the NAND gate. There are two inputs A and B. Uh, there is a same construction like AND gate, but only there is a buffer uh, here, NOT gate here. Then uh, same function like a, it's same function like a AND gate, but only complement of the inputs are there. So x is equal to AB complement, and truth table of this is inverted to the AND gate. So NOR gate is also there, whereas A and B is the input and X is the output. X is equal to A plus B bar. A plus B bar means uh, our OR gate says X is equal to A plus B, whereas NOR gate says X is equal to A plus B bar, means whenever 0 0 is the case, then only whenever 0 0 is the case, X is equal to 1, whereas uh, anything is case, X is equal to 0. Where XOR gate is used for comparison purpose, we see it later, uh, whereas A and B is the input and X is the output. X is equal to A XOR with B is the function of this uh, gate, or X is equal to A bar B plus A B bar is a function of XOR gate. XNOR gate is the inverted of XOR gate, whereas function of X is equal to A XOR with B bar. His truth table is also inverted to the XOR gate. Now, whenever we learn digital electronics, Boolean algebra is there. Algebra with binary Boolean variable and logic operations. Boolean algebra is useful in analysis and synthesis of digital electronic circuits. Input and output signal can be represented by Boolean variables. Function of the digital logic circuits can be represented by logic operations, that is Boolean functions. Uh, from Boolean functions, logic diagram can be constructed and or and inverter. So using these basic building blocks or basic gates, we can easily construct various types of circuits using Boolean algebra. And if the circuit is very large, then we can easily convert it into small by the Boolean algebra functions. Uh, then truth table is the one point. The most elementary specification of the function of the digital logic circuit is truth table. Truth table describes the output values of all the combinations of the input values called as minterm. N input variables, then 2 raised to n minterms. Uh, by this circuit, we can easily, by this slide, we can easily understand that points. The truth table, then Boolean function, then logic diagram. So truth table is suppose that there are three variables. There are three inputs x, y, and z, and one output. So conditions are 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 1 0 1 1 1 0 and 1 1 1. So there are seven possible conditions, eight possible conditions. So for that, the function is given as uh, whenever 0 0 1 is input, then output is 1. Whenever 1 0 0 is input, then output is 1. Whenever 1 0 1 is output is 1. Then using this function we can easily find f is equal to x plus y bar z, means here x into x this plus sign means the OR gate, this bar y bar means AND gate, and this y bar z means here is AND gate, y bar means NOT gate. Okay, so we require y bar, y complement means we require NOT gate here, not get here, uh, and y into z we done with the AND gate, then uh, or x into y bar into z is done with this OR gate, and the final function is our x is equal f is equal to x plus y bar z. So some of the basic identities of Boolean algebra, we see these rules in our first year book of BCS or BSc. So first rule is x plus 0 is x plus 1 is 1, x plus x is x plus x bar is 1. Whenever I say plus here, then it is OR function, or I can also say x or with y, it is also equal to y or with x, or we can also say x dot 0 is 0, x dot 1 is x dot x is x, and x dot x bar is 0. X plus y plus z is also x plus y plus z. Uh, x into y plus z is equal to xy plus xz, same as mathematical properties. X plus y whole complement is equal to x complement into y complement. It is De Morgan's law. X complement of the complement is only x, so complement are cancelled each other. Then 10th formula is xy is equal to y into x. 12th formula is x into yz is also written as xyz. 14th formula is x plus yz is equal to x plus y bracket and x plus z bracket. So 16th formula is xy bar is equal to x bar plus y bar, means product of the complement is equal to sum of its complements. It is De Morgan's law. So usefulness of this table for this table is very important for simplification of Boolean functions, derivation of equation, derivation of equivalent Boolean functions, ordinary and or and inverters. But certain different form of Boolean function may be convenient to obtain circuits with NAND NORs applications of De Morgan's theorem. So this is the again here I have given De Morgan's theorem, that is product of the complements are is equal to sum of its complement, and complements of the sum is equal to product of its complement. So in digital system, number systems are very important, such as decimal number, binary number, octal number, and hexadecimal numbers. For a decimal number, after hearing word number, we immediately think of most familiar decimal number system with its digit 10, such as 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. However, it is only customarily and not necessary to use these symbols. Basically, a number system is ordered set of symbols known as digits, and the total number of symbols used in system defines the type of number system. Some of the commonly used number systems are binary, octal, hexadecimal. Uh, Binary number whose base are 2 because of the two symbols are used 0 and 1. Octal number systems are base are 8, as the name indicates octal. So symbols are used 0 to 7. Hexadecimal number systems base is 16. Symbols are used 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So each number system has a predefined rules for performing arithmetic operations like addition, subtraction, multiplication, etc. So numerical value of symbol in different positions. Suppose the number is 1100, then in binary it is uh, last bit is LSB and its position is ones, then second last is twos, fours, and eights. So last zero digit is MSB, and first one digit is MSB, LSB, and MSB. So binary 1100 is equal to decimal 8 plus 4 is equal to 12. So binary to decimal conversion, uh, suppose binary number is suppose binary number is 110011, then its decimal equivalent is 32 plus 16 plus 0 plus 0 plus 2 plus 1, it is 51. So also decimal to binary conversion, uh, for decimal to binary conversion we can use divide by 2 process, and there is a suppose we want to see the 13 decimal number into suppose we have to convert 13 decimal number into binary. So 13 divided by 2 is 6, remainder is 1. 13 divided by 2 is 6 divided by 2 is 3, remainder is 0. 3 divided by 2 is 1, remainder is 1, and 1 divided by 2 is equal to 0, remainder is 1. So reminders are taken in this way, and this digit is constructed. This is the binary equivalent of decimal number 13. So in electronic translators, the devices that converts decimal to binary numbers and from binary to decimal numbers is called as electronic translators. So in digital electronics, there are encoders and decoders. Encoders translate from decimal to binary, whereas a decoder translate from binary to decimal. Encoders means the circuit which translate known numbers, means we can use the decimal numbers in our day by day life, but not the binary number. Means known to unknown number translation is encoder, and decoder means unknown to known number translation, means decoder translate from binary to decimal. we see one by one. Decimal to BCD encoder. Now decimal number we have known and BCD number are unknown. BCD means binary coded decimal. It is 4-bit number. So truth tables are made with uh, the help of this truth table. Equations are made. Then equations are y is equal to d1 plus d3 plus d5 plus d7 plus d8. Then these are the inputs, and y0 is the output, y1 is the output, y3 is the output, y2 is the output, y3 is the output. These y outputs are the BCD equivalent of the uh, decimals. So with these equations, we can easily construct the circuit, decoder circuit. Here is the decimal numbers, and here are the switches displayed in this manner. Uh, First of all, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and here is the 5 volt means logic 1. Logic 1 is applied to this, and there are OR gates. When 0 key is pressed, A, B, C, D are 0 because all the switches are open circuit. When 1 is pressed, 1 line is connected to 5 volt, and 5 volt is connected to this D point, uh, uh, D OR gate. Then D is equal to 1, means 1 is, whenever 1 is pressed, then BCD output is 0 0 0 1. When 2 is pressed, then 2 line is connected only to the this second last OR gate. Then only the C output is 1. Then A is 0, B is 0, C is 1, and D is 0, means 0 0 1 0. Our BCD2 is displayed on this manner. So we can easily construct this circuit. This circuit is used in telephone system, whereas 0 to 9 keys are there, and whenever we press 0 or 1 or 2 or anything, any key from our dashboard, then there is a binary data is inserted into processor, or processing on the equivalent data is there. So for demonstration purpose, this is the keyboard of key. If we press 0, then binary input is there is 0. If we press 5, then binary input is 0 1 0 1. If we press 7, then binary input is 1 1 1 1. Okay. If you press 3, then binary input is 0 0 1 1. So there is a decimal to binary encoder. Encoders are available in IC form. Uh, these encoder translate decimal input into binary BCD outputs, as you see. Now next is the BCD to 7 segment decoder. This is the decoder, uh, BCD to 7 segment decoder. We always see the 7 segment displays on various places such as railway stations, etc. In these 7 segment displays, there are watch, uh, clock, or token number system are there. So there are two types of displays. One is a common anode and other is a common cathode. There is a diode like structure, but there is missing arrows. So consider that there is a arrows at this place. Mm, A, B, C, D, E, F, G are the LEDs of the 7 segment displays. So in the common anode, anodes are common and connected to plus volt, means logic high, whereas in the common cathode, cathodes are connected to each other, and kept ground or low logic level. So whenever common anode LED, we want to on the common anode LED, then we have to place for common anode. If we place A is equal to 0, B is equal to 0, then these two LEDs are uh, turned on. Whereas for common cathode displays, whenever we uh, whenever we apply the logic 1 at A and B, the equivalent display digits or equivalent uh, LEDs are turned on. So uh, there is a IC form of a BCD to 7 segment decoder. In this BCD to 7 segment decoder, there are four inputs, BCD inputs, and one clock input. Then A, B, C, D, E, F, G are the output, are connected to this type of 7 segment LED display. So for making this block, it is unknown to us what is inside this BCD to 7 segment decoder block. For make this circuit, we want to draw the truth table or logic table for this appropriate circuit. So decimal digit is 0, then BCD, when BCD input is 0, decimal digit is 1. For so equivalent LEDs are here displayed on the logic table. So by using these this logic table, we can easily draw K maps. Uh, Now by using K maps, there are various types of equations are there. We found 7 equations from A to G, and by using these equations, our inputs are binary BCD, B0, B1, B2, B3, and B0, B2, B3, and this is the circuit. This circuit is a we draw this circuit by using uh, equations found from Karno map. Now, if the binary input is 0, 0, 0, then our display is displayed on 0. See that there is A, B, C, D, E, F. Only G is off. Then we visualize that we visualize that there is a 0 when BCD inputs binary input is 0001, then only B and C LEDs are on. Whenever we apply binary input 010 0010, then two displays, three displays, and so on. So electronic decoders are also available in IC forms. These decoder translate from binary to decimal. Decimals are shown on a 7 segment LED display, and these decoder also drive the 7 segment displays. So next number system is a hexadecimal number system. It uses 16 symbols. So base of this this system is 16. So 0 to 9 and A, B, C, D, E, F. So in decimal, we count 0 to 9, and after 9, 10, 11, 12, 13, 14, 15, 16. But in binary, we but in hexadecimal, we count 0 to 9, and after 9, A, B, C, D, E, F. After F, the 16th number is 10, 11, 17th number is 11, and so on uh, to the 19. And then after 19, the 1F, 1A, 1B, 1C, 1D is there. So these are the hexadecimal systems. So we can also convert hexadecimal number systems into binary number systems by uh, just placing its equivalent binary bit. So C is 12 and 12's binary is 1100 and 3 is 0011. So 11000011 is the binary equivalent of the hexadecimal system. Binary to hexadecimal conversion. So easily we can construct binary to hexadecimal conversion. A binary is 1110 means 8421 is 12. There is a E 12 plus 2 14 E and 1010 is 10A. So for a decimal to hexadecimal conversion, it is a divide by 16 process. And if we if you convert 47 into hexadecimal, then 47 divided by 16, because of the hexadecimal base is 16. 47 divided by 16 is not happen. There is a 15 remainder and result is 2. Whenever the 2 divided by 16 is not possible, 0, remainder is 2. So 2f is the resultant hexadecimal number of this 47 binary decimal number. Now for hexadecimal to decimal conversion, easily we place 16 raised to 1, 16 raised to 2, 16 raised to 3, 16 raised to 0, 16 raised to 1, 16 raised to 2. So it is 1, 16 and 256. So hexadecimal number is 2dB. So hexadecimal number is 2dB. 2 into 256 plus D is 13. 13 is into 16. B is the 11. 11 is into 1. Resultant decimal number is 731. So as the hexadecimal number system, octal number systems are there. 1, 2, 3, 4, 5, 6, 7, 8. So as decimal numbers, 1 uh, here is the decimal octal numbers 1 to 6, 7, and after 7 it is 10, 11, 12 till 17. After 20 means 8 and 9 is not there. So in the digital circuits, digital electronics, various equivalent circuits are there. If we want to construct a function, f is equal to a b c plus a b c bar plus a bar c, this can be solved or this can be reduced to uh, the ab plus a bar c, but there are a few steps uh, in this second case. AB C plus C bar means C is the common and we take it common, plus AAC. So C plus C bar is 1. We see in the Boolean functions, Boolean law. So A bar dot 1 plus A bar C is the final result. So if we make a function circuit of the first function, then this is the circuit. First circuit is the first is of the first function. Then second circuit is the second function. Uh, Here I denotes, and third circuit is our final minimized function. So the need of Boolean law is to minimize the function. See, there is a 1, 2, 3, 4, 5, 6, 6, 6 logic gates are required for first function. Then again 1, 2, 3, 4, 5, 6, 7, 7 required for second function, but only 4 logic gates are required for last function. So simplification is done by those. So next building blocks of our digital electronics are flip-flop. There are two stable states. Flip-flops has a memory capability. Operation is specified by a characteristic table. So there is a 0 state and 1 state. We always use them for 0 state. If output of a NOT gate, upper NOT gate is 0, then this NOT gate's output is again connected to the of the input of the NOT gate, and because of the NOT gate it is inverted, and again it is connected to the input of the NOT gate. So it is 0 state, and for 1 state, if output of a upper NOT gate is 1, then it is connected to the input of a lower NOT gate. Because of the lower NOT gate, input is 1, output is 0 because of inverter, and this is again connected to the upper NOT gate's input. In order to use the computer circuits, state of flip-flop should have terminals and output terminals so that it can be set to certain state, and its states can be readily externally. So first flip-flop is RS flip-flop, whereas two OR gates and two NOT gates are there. So R and S inputs are connected. Whenever S is 0, R is equal to 0, and whenever S is equal to 1, S is equal to 0, output is equal to 0, and S is equal to 1, output is equal to 1. Whenever there are both are 1 1, then it is known as intermediate or forbidden. Whenever both are the zeros, then output follows the previous state. So clocked flip-flops are also there in large digital system with many flip-flops. Op- uh, Operations of individual flip-flops are required to be synchronized to clock pulse. Otherwise, the operations of the system may be unpredictable. So, for connecting each flip-flop to one flip-flop to the another flip-flops, the clock is done synchronization job. Clock pulse allows the flip-flop to change state only when there is a clock pulse appearing at the uh, clock terminal. So these are the blocks of the SR flip-flop. Uh, Operates when a high. There is a small difference in these two uh, diagrams. There is a clock, direct clock is given to the uh, SR flip-flop when it is operate is clock is high, and there is a bubble, means there is a NOT gate is connected to the input of clock, therefore it operates when clock is low. So what is clock? Clock is the simply clock is the square wave pulses. RS latch with preset and clear inputs. So these two inputs are additionally applied, preset and clear. Preset means for setting the flip-flop output of the flip-flop to the 1, and clear means clear the output of the flip-flop to the 0. Uh, so Again, there is a modification of RS flip-flop. There is a NOT gate is connected between R and S, and enable terminal is there. So enable means clock terminal is converted to the enable terminal, and there is a D flip-flop is made by uh, the various types of gates. So D flip-flop, in D flip-flop, when D is 0, Q is 0. When D is 1, Q is 1. But D flip-flop follows the clock input. Whenever only clock pulses appear, or age triggering of a clock is appear, then D flip-flops will toggle 1 to 0. So what is age triggering? In latches, latches responds to high or low periods, whereas flip-flop responds to edge triggers. So positive edge means whenever the pulse is transient from 0 to 1, there is a change in the pulse 0 to 1. That time only the output changes of the appropriate flip-flops. So here is the positive edge triggered D flip-flop and JK flip-flop is shown here. So if we want to count some pulses or clock pulses, or if we want to design and circuit which is if we press a button and there is a count is happening, means I press one button once, then count count 1. I press that buttons again, that counts 2. I press that button again, that counts 3. Then there is a synchronous up counter circuit is made. So there is a we first construct a desired count table, then we have the excitation table of JK flip-flop, then we draw the transition table, and from this transition table the K map is drawn. By using these K maps, we can easily find our outputs, our equations of the equations to design the circuits. Then finally we design the circuit, and whenever here the clock is shown, and J and Ka, there is a JK flip-flop is used uh, in D mode, where J and K are common. Whenever J and K is equal to logic 1 of a first flip-flop, then clock pulse is applied. Whenever first clock pulse is appeared, or here is the small bubble at the clock input, means it is the negative edge triggered flip-flops. Whenever first negative clock pulse is applied, then there is a count 0 0 0 0 0 1. Whenever second clock pulse is applied, 0 1 0. Whenever third clock pulse is applied, 0 1 1, and so on. There is a 1 1 1. It counts 0 0 0 to 1 1 1. So there is some registers are there in digital electronics. Register uses to store the binary bit or binary information for long time. Uh, there is a sequential circuit counter. There is a memory components, whereas these uh, you can see there is a one rack type structure here, word or bytes. Means whenever we construct registers, if we construct 8-bit register, then the 8-bit register stored 8 byte of memory. Each word has a here is the we can easily see that random access memory. Each word has a unique address. Access to word requires some time independent of location of the word. There is a organization you can see k address lines, read and write inputs, then end data input lines and end data output lines are there. So we can easily construct a ROM, means it is a read only memory. It performs read only operation only. Write operation is not possible. Mean if we construct a ROM, uh, during construction there is a memory download function. uh, that is a combination. Suppose we want to download these combinational circuits displayed here, these combinational functions displayed here. We have to convert into canonical minterms, then convert into logical, and then these X out ABC inputs are downloaded into the ROM. Means construct a ROM in that manner. So types of ROM are store the information function during production, mask is used in the production process, unalterable, and low cost and large quantity production used for final products. So these are ROM. Uh, some ROMs are programmable, means random access memory are programmable again, store into electrical using programmable uh, PROM programmer at the user side. It is unalterable and it is higher cost than ordinary ROM. Used in system deployment phase, can be used in small quantity system. And nowadays we can use EEPROM or electrically erasable ROM, EEPROM. It is stored electrically using PROM programmer at the user side. Stored info is erasable using UV light. Uh, Higher the cost of PROM but reusable. Used in the system deployment phase, not used in the system production due to erasability. So some of the types of integrated circuits are there. Uh, TTL, ECL, MOS, CMOS are the technology, and circuit classifications by circuit density. It is small scale integration, several less than 10 independent gates. There are 10 gates only in the SSI. In MSI uh, integrated circuits, 10 to 200 gates perform elementary digital functions, decoder, adder, register, parity checker, etc. Large scale integrations, 200 to few thousand gates, and nowadays we use VLSI, thousands of gates of digital systems, which is used in microprocessor, memory module, etc. So next topic is the architecture of memory. In this topic, we will see that row decoder, and there is column sense, mux sense. Uh, there is a blocks are you this diagram is shown is in blocks. So one block is one register, and there is a 2 raised to m plus k bits. For example, let 1048576 and m is equal to 8 bits for 1 million byte of memory. So for 1 million byte of memory, n is a very much large number. So there is a memory hierarchy. Uh, the total number memory capacity of a computer can be visualized by hierarchy of components. The memory hierarchy system consists of all storage devices contained in a computer system, from the slow auxiliary memory to fast main memory and to smaller cache memory. So there is a auxiliary memories such as a magnetic disk and magnetic tapes. Then there is a primary memory, that is main memory. There is a cache memory and a register memory. The outside of system is used in magnetic disk and magnetic tapes. So if we say that the fastest memory is at the topmost, that is register memory, then slowest memory is the magnetic tape memory. So there is a triangle which shows the speed of the memories. So memory unit is an essential component in any digital computer, as it is needed for storing programs and data. A computer is equipped with a hierarchy of memory subsystems, some internal to the system, directly accessible by a processor, and some external accessible by via input-output modules. External memory consists of peripheral storage devices such as disk and tape that are accessible to the CPU via input-output controllers. External memory can also be referred as a secondary memory, as auxiliary memory. Internal memory is equated with the main memory, but there are other forms of internal memory, like CPU requires its own local memory in the form of registers. Inside of CPU, there are registers and memories. Internal memory is also called as a main memory or primary memory. So two types of memory, volatile and non-volatile. RAM is the volatile memory. Volatile means the data can be read and written in the RAM with the help of address of location. Volatile means the memory is vanished when power supply is switched off. And non-volatile means memory not lost when computer is power down. ROM is the best example of non-volatile memory. There are three key characteristics of memory: cost, capacity, and access time. The greater the capacity, smaller the cost per bit. Greater the capacity, greater the access time. And smaller the access time, greater the cost per bit. Means if the memory is fastest, then cost is obviously high. Then there is some types of memory: RAM, ROM, PROM, EPROM, flash memory, and electrically erasable memory. So in digital systems, there are memories, and there is a few specifications of memory, that is access time, speed, capacity, cost. So memory capacity is the number of locations that exist in given memory. Memory capacity is measured in bits, or we can say byte or word. When word are used, the length of word in bits of byte has to be given. Means we can say kilobytes, gigabytes, megabytes memory capacity. Memory access time is the time that separates sending a memory access request and reception of the requested information. The access time determines the literary speed of the memory. uh, the access time is small, faster the memory. Okay. So cycle time, it is the shortest time that has to elapse between consecutive access request to the same memory location. Memory transfer rates, that is it is the speed of reading or writing the data in given memory. It is measured in bits per second or bytes per second. Now next is the computer organization. Inside the computer, there is a some systems organized in this manner. There is a CPU, memory, and input output. So CPU is connected to the all of these devices and communicate. CPU only gives the address. CPU not require address from memory and input output devices. So only one directional arrow is there. CPU get control, CPU get data and give data to the various memory and input output devices. So there is three buses: control bus, address bus, and data bus. So we can see in detail. Address bus is the group of wires or lines that are used to transfer the addressable memory or input output devices. It is unidirectional. Data bus, as the name tells, that it uses used to transfer the data within microprocessor and memory input or output devices. It is bidirectional, uh, as a microprocessor requires to send or receive the data. The data bus also works as address bus when multiplexed with lower order bus. Data bus is 8-bit long. Control bus. Microprocessor uses control bus to process the data. That is what to do with the selected memory location. So there are so many things that can say in this webinar, but due to time constraint, I can skip those. Uh, so in earlier days, there is a uh, computer. The first counting device was the abacus, originally from Asia. It worked on place value notion, meaning that place of a bead or a rock on the apparatus determining how much it was worth. There is a two types of abacus is there: Roman abacus and Russian abacus. Napier bones in 16th century, Pascaline in 1643 42 century. So this is the device, mechanical device. This is the mechanical device or machine, calculating machine could add and subtract two numbers directly and multiply and divide by repetition. Then in 1820, difference engine is comes. Charles Babbage, father of the computer, designed this machine. This is the also mechanical machine. It is fully automatic and command by fixed instruction program. Then in 1814, Adalonce Dolans is developed first computer programmer, provided the first algorithm intended to be processed by Charles Babbage, early mechanical general purpose computer, analytical engine. She suggested that binary systems should be used for storage rather than decimal system. So 1815, uh, George Boole uses Boolean logic in mathematics that revolutes re- huge revolution is come in digital logic. Then Henry Tabler's in 18th, 1819, uh, Hermann Hollerith introduced first electromagnetical punched card data processing machine, which was used to compile information for 1819. Uh, then in 1906, the vacuum tubes is invented by American physicist D. Forest. Uh, by using these vacuum tubes, there is a computer is made. Then Howard Mark I, in collaboration with engineers from IBM, constructed a large automatic digital sequential control computer called as a Howard Mark I. This computer called handle all four arithmetic operations. Then first computer is there is a ENIAC. ENIAC first. Electrically numerical integrator and calculator machine was developed by John W. Mochi. Uh, then first generation of computer in 1915 to 1959. There is a integrated circuit was developed by Jack St. Clair Kelby and Robert Noyce of Texas Instrument manufactured first integrated circuit or chip, which is a collection of tiny little transistors. So using transistor, you can say that this image, in this image, using tiny little transistor, first integrated circuit IC was developed. In second generation, 1959 to 1965, there is a first general purpose digital computers to use integral circuits, and programming language was developed, COBOL. So in third generation, 1965 to 1971, internet is started in 1969, and 1917 there is a famous Intel chip 4004 was developed by Ted Hoff. 1971 Intel released first microprocessor specialized integrated circuit, which was able to process 4 bit of data, uh, only 4 bit of data. It also includes its own arithmetic logical unit, Pascal. Uh, so in fourth generation, 1971, uh, then there is a revolution in the computers was continued in 1993. There is fifth generation, present and beyond. There are fifth generation computer. You can see that there is a Raspberry Pi. It is a fifth generation computer. It is a smartphone card type computer. Raspberry Pi is single board Raspberry SBC single board computer. Raspberry Pi Foundation registered as a UK-based educational charity. The aim of the foundation is to provide low-cost, high-performance computer capable of creating modeling-specific applications. So this computer, you can see on display, is only of a credit card size, which can be plugged into a monitor, and it acts as a mini computer by connecting keyboard, mouse, and display. Raspberry Pi 3 is based on a Broadcom system on chip with ARM processor. Raspberry Pi is widely used for real-time image video processing, robotics, IoT-based applications. Raspberry Pi Foundation officially provides Debian-based Raspberry OS, Noobs OS, Raspberry OS in freely available OS. Raspberry have GUI, graphical user interface, which includes tools like browsing, Python programming, games, etc. Raspberry Pi provides access to GPIO for developing various applications such as LED motors, sensors, etc. Raspberry Pi provides on-chip I2C UART. So there are a lot more things that I have covered in this webinar. So thank you very much. Despite the time constraint, this point, uh, I have tried to cover as many as topics as possible. I thank all collaborators and their team for giving me these opportunities to speak here. And thank to all the participants who watched the webinar from the beginning to end. I am also thanks to Principal of the Dadapatil Rajale College, Dr. R.J. Temkar sir, for giving me this opportunity. Thank you all.
Thank you, sir, for such a nice, wonderful, and helpful information on digital electronics. Now I request Professor C.N. Pansare sir, vote of thanks.
Hello. Good morning. I have given the opportunity to thank everyone. At the start, I would like to express my gratitude to the resource person of the webinar, Professor Hamid Sayyed, for giving his valuable time today. I thank you for your lecture and also giving excellent information about electronic science. I take this opportunity to sincerely thank the chairman of the CDC, Honorable Shivajirao Rajale. I also thank principal of our college, Dr. R.J. Temkar sir, for his valuable support. I extend my thanks to president of our Sanstha, Honorable Appasaheb Rajale, his Kaka, MLA, Honorable Monikatai Raju Rajale, Honorable Rahul J. Rajale for their support and valuable guidance. My words may not be enough for communicating my sense of gratitude to all the participants for their very good response and value discussion on the topic of this webinar. Last but not the least, let me express my gratitude to OS Mr. Vikram Rao Rajale, Arts faculty in charge, Dr. M.S. Tamboli sir, Science faculty in charge, Dr. J. Newell sir, Commerce faculty in charge, Dr. H.J. Deshmukh sir, Professor R.T. Gholap sir, Dr. K.G. Gaikwad sir, Dr. Atul Chorpagar sir, Professor Ruiz sir, Professor Desai sir, Professor Sanjay Maske sir, Professor Jayashree Darandale, Professor Yogita R.Ingale, Mr. Ravindra Falke, Sapte Mama, and all my colleagues for their efforts to make this webinar a great success. I once again thank you all and declare that the webinar is over. Thank you. Thank you very much.
Thank you. Thank you, sir.